All right, hello again, everybody. Here is your 3.1 problem set video key. So number one, what is the slope of a curve at the point where x equals a? This is just that limit definition that we've talked about quite a bit. The limit as h goes to 0 of f of a plus h minus f of a all over h. And then there's just some information here that we've talked about in class. Basically, we're just going to give this a name, and we're going to call it the derivative. That's pretty much all you need to know from there, I think. So number two says differentiate. Well, to differentiate means to find the derivative, which means you do that limit definition that we just wrote up top. So we're going to do the limit as h goes to 0 of f of x plus h, which is x plus h squared, minus x squared, which is f of x or f of a. You can use a's if you want, which is what we did in the past, but really a just represents an x value. So, and then this is equal to, when you multiply this out, you get the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. If you do this correctly, everything without an h will cancel, which will allow us then to cancel an h from every term from the denominator. So our x squareds cancel, this and that. This is an h right here. And now an h can cancel everywhere, leaving us with the limit as h goes to 0 of 2x plus h, which then just gives us 2x, and that is the derivative of x squared. And then a, what is the slope of x squared? At 4, negative 3 and 0, just plug those in to the expression we found for the derivative, which is x squared, or of x squared, which is 2x, and so you get 8, negative 6, and 0. So remember, derivative means slope at a point. All right, number 3 is just giving us a different way to do the same thing. There, the alternate definition of derivative. And then on 3i, we're asked to apply that. So this is the limit as x goes to a. And now it's just f of x, which is the given function, minus f of a, which is the function with a plugged in, over x minus a. And now we got to get the x minus a on the bottom to cancel out, so we can plug in a for x, just like we wanted the h on the bottom to cancel out, so we could plug in 0 for h. So if you take this and you multiply top and bottom by the conjugate is the trick here, which we saw really only on one problem, I think, that we did earlier this year. But hopefully if you see this again, you'll know to do it. Honestly, we're not going to see this very much anymore, which is the good news, because as we get into chapter 3, we learn shortcuts to find derivatives of all these different types of functions. But if you multiply this out, you're going to get x minus a on top over x minus a. Leave the denominator in factored form, because remember, your goal is to get a factor to cancel, so you want to leave it factored. Okay, so we get that. Now my x minus a cancels, which leaves us with the limit as x goes to a of 1 over square root of x plus square root of a, which has now made a plug-inable, and you just get 1 over 2 radical a. Now, instead of using a just represents any x value, so this one's just saying, hey, really the derivative f prime of x is equal to 1 over 2 radical x. And then what is the domain of that? The domain is x has to be greater than 0. Number 4 is just some different notations for derivative. A is y prime. B, you just say dy dx, even though it looks like a fraction. We'll talk a lot more about that. We don't see that one, or sorry, A and B and D we see the most often, really A and B mostly. C we see every once in a while, in this class at least. But just know that those all mean derivative. Alright, on number 5, we need to graph the derivative. So you were to draw tangent lines at these different points. So at A, I found the slope to be 2. So remember, the derivative graph has x value, comma, the y value is the slope at the x value in question. So when x is 0, I found the slope to be 2. At point B, my slope was 1.5. At C, it's 0. At point D, I got a slope of negative 1.4. Somewhere around there, doesn't have to be perfect. At point E, my slope is negative 1.5. So about there, and then at F, the slope is 0 again. So this graph looks something like this, roughly. And then if you extended it beyond point F, it would kind of level off like this, because that part of the graph kind of looks like a line. So it would become, so the derivative graph would become horizontal, because it would have a almost constant slope. Okay, but the connections to make here that I'm looking for is when f is increasing or has a positive slope, the graph of f prime is above the x-axis right here. Because everywhere, because the y values of your derivative graph represent the slope of f. So if f has a positive slope, then f prime, which is the slope, must be positive. It must have positive y values. So when f is increasing or has a positive slope, f prime is above the x-axis. When f is decreasing or has a negative slope, f prime must be below the x-axis, because that's where the y values for f prime, which represent the slope of f, are all negative. So you must have negative y values on your derivative graph when your slope is actually negative. And then I think that's good enough for now, for that particular thing. Okay, moving on to the last page. So here we're given the graph of a derivative, and this derivative graph, there's only two different values. It either equals 2 or negative 2. And so that means the slope of our given function only has two different slopes, either 2 or negative 2, which tells us then that it's really just two different line segments. We also have the point f, we know f of 0 equals 1, so we know we have the point 0, 1. But at these x values, if you look down here, like this is telling us the slope over here, so I need a slope of negative 2. So from this point I can just go give it a slope of negative 2 and go down 2 over 1, and I know that this point also exists. But that's the x value where my slope changes, which is what this is telling me. Here we have this and this, so the slope is now going to change once we pass x equals 1. The slope is going to become a slope of 2. So once I get there, I can just go up 2 over 1, have a slope that looks like that, and now my function will look like this. And that meets all of the criteria of that problem. 7, we now know that the derivative of the function is the same as slope. Slope at a point, to be more specific, but it is slope. How can we tell if a function is differentiable at a point? You got to have the same slope from both sides. I think we've hit on this a little bit in class at this point. And because to be differentiable means a tangent line exists, but you can't draw a tangent line at a point where the slope is different from both sides. So how can I draw a single line here that matches this slope and this slope? Well, it's not possible, because a line only has one slope, and this has two different slopes from both sides of this point right here. And so that's called a corner, and so at a corner, a function is not differentiable. Sketch a function that is not differentiable at x equals 3 and explain why it is not differentiable. So really, if we just take the graph I just drew, put it on a coordinate grid and call it x equals 3. 1, 2, 3. Some random point there. It doesn't really matter where I put that. But if I make that a corner, then it's not differentiable there because the slope is different from both sides. And then C is number 6 differentiable at every x. Well, no, it is not. So this graph I drew, that is not differentiable everywhere. It's differentiable everywhere except x equals 1, because the slope is different from both sides. Now, if you look at the key, the handwritten key, you'll see how I wrote that using a limit definition. But remember, the limit, this limit definition, like the limit as x goes to 1 from the negative side, of f of x minus f of a over x minus a. This is not the limit of the function. This is the limit of what we call the difference quotient, which is the definition of derivative. So when these two, or slope at a point, so when the slopes from both sides of 1 are not equal, which is what this statement is saying in weird math notation, this is just saying, hey, the slope from both sides is different. If the slope from both sides is different, then the function is not differentiable at that point. And that is it. Thanks for watching.